So that would be amazing.
Okay, I think I'm recording now, okay?
Yes, stay recording. Yes.
Okay, so sorry for people that are not with us, at the moment right now. We just realized that we weren't recording. So now we're recording. We're doing repeated measures in NOVA. In particular, we are doing chapter 15, Smart Alex task 4, which is the one you were supposed to do, not 5. If you do 5, or we've already done 5, good for you. That's great. You're not going to get penalized for it. Okay, so repeated measures in NOVA proceeds thusly. We'll go to general linear model. You go to univariate. No, you go to repeated measures. Correct myself. We go to repeated measures. And then you get this tricky little box here that you don't get when you do an independent design. So we need to name our factor or our measures that were repeated. In this case right here, it's beer. It's pints. So let's call it like pints, or you can call it beer, whatever you want to call it. It's a way for you to understand the different treatment levels. So let's call it pints, okay? So how many levels are there? There's 4 levels. There's 1 pint, 2 pint, 3 pint, 4 pint. So we're going to tell SPSS there's 4 levels, okay? And then you hit add. And then you hit define.
Oh, I do not. Oh, I do have define.
Okay. And then what you're going to do is just select all of the pints, 1, 2, 3, 4. And then you're going to dump them over. It's asking you which one do you want to code as 1, 2, 3, 4. We're going to put pint 1 is 1, pint 2 is 2, pint 3 is 3, and pint 4 is 4. Okay?
Okay.
Yep.
Okay. Now, with regard to options over here, let's see. We'll keep it simple. Obviously, as you read the book, you can get really complicated with things you want to do. But we'll keep ours simple. So from an ANOVA, you have to do a post hoc test, right? But you can't do a post hoc in the traditional sense in a repeated measures design. If you click on post hoc, you'll see there's no option here for you. But we can get around that if you go to EM means, which is estimated marginal means. If you say, I want the pints means, but I'm going to compare the main effects, and you make it a Bonferroni test, you're essentially getting Bonferroni post hoc tests. Okay?
Where did we get that little pop-up again from?
Great. I got it from the EM means dialog right here. You go to EM means.
I don't have that.
Do you have options?
Yes.
Go to options, because you're probably on a different version. Go to options. My options is different. If you were to click on options on your screen, you'll see something similar like this. You'll say display means 4.
Right.
Dump pints over there.
Perfect.
Click compare main effects.
Perfect.
And then change it from LSD to Bonferroni.
Beautiful.
Okay?
Got it.
Great. And then go to options again and click on descriptive statistics. And then that's all I'm gonna do. Okay, and I'm gonna run it. I'm gonna hit OK. Okay. Okay. So this is where things get a bit complicated. In a repeated measures design, the output is a little different. Okay. So at the very top, we told it to give us descriptive statistics. It did. Okay. It gave us the means for each of the pints. So on average, at what point did people start eyeing up other people more? At what level of beer consumption did people eye other people up most?
3 pints.
Correct, 3 pints. They eyed up just over 15 people on average, okay? Okay, good. So, and that's above 1 pint, 2 pints, but then that's less than 4 pints, which is interesting, right? I don't know what's going on there. Maybe you get so inebriated that you can't even look at people. I'm not sure. I can't even look. Right. Okay, so that's some interesting numbers to look at. That's not a statistical test. We don't know if that is meaningful or not. So we need to proceed. Multivariate tests are something we're going to skip over for right now, but we might come back to them. It all hinges on the next box. this box right here is Mauchly's test of sphericity, which is just like the worst sounding thing on the planet. Right? Essentially, what this is testing is variances across observations. And just like in an independent samples design, we had the Levene's test to make sure that the variances within each group were not too dissimilar across groups. Mauchly's test wants to make sure that the variance between observations is not too big, so or dissimilar. You want Mauchly's test, you want this one to be not significant. Okay, so one more time. You want Mauchly's test to be not significant, but it is in this situation. You can see, look, it is less than 0.05, which is the conventional threshold, right, of statistical significance. It's below that. So we have just violated this assumption. So this is a big deal, some people would argue, although I'm sure you guys have already read chapter 15, so you know that Andy is pretty critical of Mauchly's test of sphericity. So he says to consume the test with some caution. So if you do violate Mauchly's test of sphericity, what you then need to do is walk with caution. So this next table right here is the table that we really care about. This is where the answers are. For those of you that are like really not interested in like what I have to say other than like what you need to do for your homework, this is the table that has the answers in it, or at least some of them. So this tells us whether or not there is a statistically significant difference in people looking at other people's bodies based on how much alcohol they drink, right? And so if Mauchly's test was not violated, we could assume sphericity, which means we would read just this first row, sphericity assumed. And if we were to look there, we would see that there is a difference between pints on people's roving eye. However, we violated Mauchly's test, so technically we're not supposed to be able to read from this row. So then what we need to do is figure out, well, which row do we read from? Do we read from the Greenhouse-Geisser row or the Hein-Felt row? And so you need to look up here to determine which one you want to look at. Now, there's a whole bunch of rules of thumb. Your textbook lays them out for you. If Greenhouse-Geisser is less than 0.75, people say read Greenhouse-Geisser, in which case there is a statistically significant difference. Some people will say, oh, but that's a stupid rule of thumb. You should go with Hein-Felt if it's, I think, greater than 0.5. Okay, in which case we're also still statistically significant. Other people will say, well, why don't you just take the average of the two, in which case we still are statistically significant. Okay, do you see that?
Mm-hmm.
Okay, so there is evidence to suggest that there is a statistically significant difference between the groups. Now, an alternative is to look at the multivariate test. If you violate Mauchly, some people will say, well, you could look at Greenhouse-Geisser or Hein-Felt, or you could look at the multivariate test. Now, this is where our life gets even more complicated, because we looked at Greenhouse-Geisser, we looked at Hein-Felt, they were all statistically significant, indicating that there is a difference between pint treatment. But the multivariate test is not statistically significant. So then we're kind of in a pickle. On the multivariate side, which is a very robust test, it would indicate that there is no difference. But if we look here at sphericity assumption, Greenhouse-Geisser, and Hein-Felt, it does look like there's a difference. So my advice to you is to proceed in the analysis, but to be aware of the fact that we have violated this important assumption, okay? And then we have looked accordingly at different tests, such as Greenhouse-Geisser and Hein-Felt. And so based on that, we're still interested, we're moving forward. So we're walking forward with the assumption that there is a difference between the pint treatment groups.
Question.
Yeah.
At the top where the syntax appears,
Yep.
does it say, oh yeah, yours also says warning. What's that for?
It's something about the Unicode encoding mode. I don't know. I doubt that you guys will even get that warning. I'm not sure. Did you get that warning?
Yes, I did.
I got that warning too, so that's why.
Yeah, I'm not. I don't know what's going
But
on.
so that's basically the syntax that we're copying for Smart Alex.
I would not copy this one because in order to do it, you have to double click on it to get in there and copy it. It's just kind of a pain in the butt. What I would do to get the syntax for your Smart Alex is to, instead of when I did the test, when I set it up, I hit OK.
Right.
For you, I would hit paste, and I would just copy that.
Okay, but they're the same, right?
This is truly your syntax right here. This is a syntax.
All the other ones the other way.
I've been going through the whole thing using this.
Are we safe?
Yeah, it's fine. You can do the other way. It's just a pain in the butt. This is easier. This is the better way to go because as you do an analysis, if you paste everything, it will build a very, 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 very long file of syntax for you. Whereas if you go here, you have to manually build it yourself. But you're right. Like if I was to take this, copy it, and if I was to go back to my syntax window now, and if I was to paste it, you can see if I were to highlight it and if I was to run it, I get the results again.
Okay, but we're safe if we've done it the other way.
You're safe. You're safe. You're just you're doing more work for yourself.
We're doing more work, but that's okay. Okay, perfect.
Okay, so there does look like a difference. There's a difference in people's eye, eye roving based on how much beer they drink, but we don't know where. Is the statistical difference between 1 and 2 pints, 2 and 3 pints, 3 and 4 pints, 2 and whatever it might be, 2 and 4 pints, and so that's where the post hoc analysis comes in. Remember, we told it we wanted the pairwise Bonferroni comparisons, and you can see here. Looking at the Bonferroni comparisons, there does not appear to be any differences between 1 pint and 2 pints, 3 pints, and 4 pints. There does appear to be a difference, however, between 2 and 3 pints. And the only reason I know that is because I'm looking at the p-values right here. Okay? See how it's less than 0.5? Yeah. And how do I interpret this difference? See this -3? This tells us that people who when you drank 2 pints, you looked at roughly 3.5, maybe 4 people less than when you drank 3 pints. That's what that is telling us. But interestingly, that's the only difference. It's from 3 to 2, which is really interesting. And I don't know, just for further analysis, if we wanted to, we could plot this out. I'd be interested to see. Oh, I'd have to restructure the variable. Never mind. I'd be interested to see like what the means look like. Do they give us a mean here? I wonder if they give us a mean plot option here. Oh. Last add or two. No. Okay, we have to set it up in a different way. But yeah, you can see that there's really no difference between drinking 2 pints, 1 pint and 2 pint, 3 pint and 4 pint. The real difference is 2 to 3, which tells me that like, I don't know, let's think plausibly about this. Like there's no real difference between your propensity to look at other people's bodies when you drink 1 beer and 2 beers. But and maybe that's because you're not really that inebriated after 1 and 2 beers. But when you go from 2 to 3, there is a big difference. All of a sudden, then maybe you start like loosening up and your inhibitions kind of go away. So there's a difference between 2 to 3. There's no difference between 3 and 4, which is interesting. So it tells you like, once you cross the 2 beer threshold, you might as well just keep going, right? Like you're just eyeing people up. There's no difference. Like you're after 2 beers, you're eyeing more people up, and there's no statistical difference based on more beers. So just keep on drinking. There's no real difference there. That's what that is telling us. Okay.
Okay.
So that is the results of the repeated measures of NOVA. Task 4, chapter 15.
What we would put then is the syntax, and then which charts would we put the pairwise comparisons, and then we did the Mauchly's test of sphericity.
Yeah. Yeah, if this was my homework, if I was doing this for the class, I would obviously have the syntax in there. I don't need that much spacing because that's ugly. Okay. I would want to include, you'd want to include copy as image.
Mm-hmm.
You're going to want to include that in there. You're going to want to include that in there. Copy as image. You might say something like an examination looking at Mauchly's test of sphericity, we found that results indicated a violation of the assumption. Therefore, we proceeded with caution, looking at the greenhouse Geiser assessment because the greenhouse Geiser epsilon statistic was less than 0.75. Okay, and we have the next table. Okay, and then you can articulate what this table now means. Results from the GG estimate indicated that there were statistically significant differences in I roving across pint levels. And then we want this one. To determine where the statistical differences occurred or were present, we looked at Bonferroni post hoc analyses. Results showed that there was no statistical, or I would focus on the only one, that the only statistical difference in I roving behavior was between 2 and 3 pints, something like that. Okay?
Perfect. And now just another quick question. When you want us to submit the Smart Alex tasks, I've been putting them all in one Word document. Should we do one Word document for chapter 1, task 5, and
No.
pile it on in one big long tome?
And then I'm assuming you want that Dropbox to you or emailed, compress it.
Oh, let me figure that one out. Let me figure out what's easier.
Okay, perfect. But at least it can all be done in one long document.
Just dump it all in there. Just keep it going.
Perfect.
Just make sure you get any clear headings, like chapter 10.
Right. Okay, perfect.
Cool. Let's see. Let me check Flipland. Woo!
Oh, we're over your time.
I'm going to send another text message. Hang on. $10 minutes, okay?
Okay.
10 more minutes, okay? And then we'll find another time to do this again.
Perfect.
Okay, so what's next? Which one do you want to do next?
What do we have on our list?
Went back to 8, wasn't it?
Chapter 8, and we were confused all in all with chapter 8.
Yeah, but is that the one with the 5 questions or no?
Chapter 8.
Yeah.
That's correlation.
1, 2, 6, and 7. We
Cool.
couldn't figure any of them. Well, because the first one, and then from the second one, from task 2, we had to gather from task 1. So it was like if we couldn't figure out task 1, we felt like we couldn't.
Oh.
get to the other ones.
Okay, so this is chapter 8, right?
Yes.
Yeah.
Yeah, so correlation. Okay, cool. So these are actually pretty easy to do. We can do all of these real quick.
Whoa.
Well, if you say so.
I didn't mean it. I didn't mean it that way. I meant easy, like in the computer, not easy to wrap your head around. I didn't mean that. I know they're hard in that way. Okay. So, so correct me if I'm. I just want to make sure because we have different versions of the book. So my book version says task 1 is a student was interested in whether there was a positive relationship between time spent.
Yeah.
Yes.
Right. Okay. So we need to pull up the essay marks data file. So I'm going to do that now. Essay marks. Okay. So essentially what we're trying to figure out is if there's a correlation between the time you spent writing an essay and then the grade you got. Okay? Now, the interesting thing is that the grade you got is measured in 2 different ways. First is the percentage on the essay, and then the second is a categorical measure of your rank in the class. Best, worst, or second, okay? So reading the chapter, you probably saw that correlation in the strictest sense of the term means looking at the degree to which 2 variables are related, and those 2 variables need to be continuously measured. So like 0 to 100 as a percent, and then like 1 to 1,000 and something else. So they need to be continuously measured. If they're not, like for instance, your grade rank in the class, like are you first class, second class, or third class, then we have to do a different type of correlation. Okay, and they're all relatively easy to do in the computer. So we can do those right now. So first things first, using the data, find out the relationship between the time spent doing an essay and the eventual mark in terms of percentage and degree class. So let's do percentage first. So to do that, we would go to analyze, we would go to correlate, and we would go to bivariate because we only have 2 variables. If you have more than 2 variables, you might want to go into partial. But
technically we have 3 variables, but we're only measuring the relationship between 2 right now.
Well, 2, right, exactly, because they want us to look at, we have 2 outcomes or 2 ways of measuring grade. One is a percentage and the other one is a categorical. Because those require different tests, we'll just tackle one first and then the second.
Perfect.
So first we're going to look at the relationship between essay grade as a percentage and then the hours you spent doing it. And because both of those are continuous, as evidenced by the 2 metric marks here, we can do that as a Pearson correlation. Okay? Pearson. And after I do this, what I'll do is I'll swap out essay and I'll put in grade. And then that, I can't do as Pearson, I'll have to do as Kendall's tau. Okay? So let's do the easier one first. I mean, they're both relatively easy. Okay? And we hit OK. Now, in contrast to all that crap we got from the repeated measures ANOVA, this is all you get for correlation. So simple, clean, easy to interpret. All you look at here is the correlation between essay mark as a percentage and hours spent on the essay. You see here, right? You don't want to look here. These would be perfectly correlated. Let's see this 1, that means they're perfectly correlated. Hours spent on an essay is perfectly correlated with hours spent on the essay. They're the exact same thing. And by the way, I should say that Pearson correlation coefficients go on a scale from -1 to +1. Okay, let me actually stop sharing real quick. Let me see if I can watch this. Okay. Can you all see that?
Mm-hmm.
Yeah.
Okay. If something is perfectly correlated, in other words, R equals 1, as X1 goes up, X2 also goes up. That is a perfect positive correlation. Okay?
Right.
If something is a perfect negative correlation, that's a 0. Oh my gosh, there's Control Z on this. This is amazing. Okay. Then as x2 increases, or decreases rather, x1 increases. That is a perfect negative correlation, okay? Now, if something is r equals 0, there is no correlation at all. Do you see that?
Yeah.
As x1 increases, x2 does not increase in any meaningful way. There's no relationship here, okay? This right here is umbrella sales, rain. As it rains, I sell more umbrellas. See that? This right here is your weight and your exercise. See that?
Yeah.
This is how much hours you spend watching television and the temperature outside.
Okay.
Although actually they might be correlated.
Yeah.
Now that I think about it, I mean, if it's freezing outside, you're probably going to watch more television. Shoot, let's think of a better example. This says hours you spend watching television and
Number of meals you have. I don't know.
yeah, right? Like what's something completely uncorrelated, right? Like the murder rate. I don't know.
Oh, yeah.
Okay, I don't know. You guys follow me though, right?
Yeah.
Yes.
Okay, cool. So now let me go back to sharing my SPSS output with you. So you can see here that essay mark and hours spent writing the essay was correlated at 0.26. So that's a very, very weak correlation because remember when something was correlated at 0.0, there's no correlation at all. This is correlated at 0.26, so it's damn close to 0, right? And furthermore, it's not statistically significant. In fact, you can plot these things. If you go to scatter dot and you go to simple scatter, you can say, I want you to plot hours and essays, just like I did with you guys on the board. And look, there's not really any correlation, right?
Right.
There's like somewhat of a slope. Like I might have the tendency to like want to draw the line that way, but I can't really. It's more like right here. And in fact, I think you can tell SPSS to put a line of best fit.
Right.
That's a really weak slope. Okay, so part one of the answer is done. Okay, we have to do it now again for the other outcome, which is measured categorically. So we go to correlate, bivariate again. Let's take out essay as a grade in terms of percentage and put in essay grade in terms of like your rank in the class, were you first, second, or third. Now, to do that, you just unclick Pearson, click Kendall's Tau, or Spearman. Kendall's Tau is what I was always trained to do. You do Spearman when you have an ordinal measure, which I guess grade in the class first, second, third is kind of ordinal. Maybe we could do both. You could do both. And you hit OK. And the same interpretation applies. -1, perfect negative correlation. +1, perfect positive correlation. And what do we see? We see that Kendall's Tau, there is a very, very weak negative correlation. And Spearman's row, there's also a pretty weak negative correlation. And neither of those are statistically significant.
Because
Okay.
again, for these, the middle, the no correlation is 0.00.
Yep, there's no correlation here.
Okay.
So again, if this was your homework, you're going to want to, you would include the scatter plot. Obviously, don't put the line through that. Don't do that because we're not doing regression here, so that line doesn't make any sense. You would include the scatter plot, you would include the Kendall's Tau or Spearman, and you would include the Pearson. And then you would say, essentially, a Pearson correlation coefficient assessment revealed that there is no correlation between the hours spent writing the essay and the final grade on it. Okay?
Perfect.
Great.
When are you available next?
Well, let's bang out number 2 real quick.
Okay, perfect.
So number 2 is on the movie The Notebook with Ryan Gosling, my wife's celebrity crush. So let's see if we go to, we need to pull up the Notebook data. Remember, I don't know if you remember this one, but this one they had males and they had females, and they had males and females both watch a documentary about notebooks or watch the actual movie The Notebook. And then they measured their sexual arousal after watching The Notebook or a documentary about notebooks. Okay, go figure. So what they want us to do in this one is to see if there's a correlation between a person's sex and their arousal level. And that's easy to do. We just go to correlate again, bivariate, and we're looking at sex and arousal. Now, notice, because I have one continuous measure and one categorical, I can't do Pearson. Well, actually, no, you're going to do Pearson because this categorical is binary. It's 0 or 1. It's sex. It's male or female. If it was male, female, and non-binary, then I would have to do Kendall's Tau. But because there's only 2 groups, you can do that as a Pearson correlation coefficient. And we call this a point biserial correlation. You just hit OK. And that's
Do
it.
we have to, like, if we wouldn't have known that, would we have to go to, like, variable view and make sure that they put the binary as 0?
I mean, you wouldn't, not necessarily. You just need to know how everyone is coded. You need to, before you hit run on SPSS.
And then we can do the same thing with the movies, right? Or the documentary and the Notebook. Are those going to be coded as 0, 1 as well, or 1 and 2, or?
Yeah, great question. Great question. So if you go and you look at your data, here we go. So the Notebook, so it looks like, yeah, it's 1 and 2.
Okay, perfect.
So you could do a point, you could also do a point biserial correlation
But
between.
we'll also run the Pearson for that one.
Exactly. So let's do it now for film. And interestingly, for between sex and arousal, there was no correlation.
Mm.
But there is a correlation between the film you watched and your arousal. And that makes total sense because one was a documentary about notebooks, like literally about notebooks. I'm not going to be, I don't know who's going to be aroused by that. But then, but the other one was about the movie The Notebook. So clearly, if you got a documentary about notebooks, you're going to have a different arousal from watching The Notebook.
I mean,
right?
there's some good-looking notebooks, but
I mean, yeah, right. I mean, right. And I also do want to point out really quick, based on what I've told you guys so far about correlations, is that a really strong correlation or a weak correlation? It's negative 0.86.
strong.
That's a
Strong.
super strong correlation.
And so we could graph it too to see then the actual line.
Well, that's the thing is the graph wouldn't make any sense in this situation. It wouldn't look very good because one variable is binary,
Yeah.
right? So, I mean, we can do it, and just for giggles, you can see what it looks like if I was to go and do a simple scatter between, we'll put film on the x-axis and we'll put your arousal on the y.
Yeah.
See,
Yeah.
it doesn't really work
Right.
because these are obviously the 2s, these are the 1s, so these are the documentary on Notebook people. No, this is the actual Notebook, and this is the documentary on Notebooks. You can see because they're obviously low arousal and high arousal. Okay?
Perfect.
So that's task 1 and 2 from chapter 8. What other one did you have? Did you have 6? What did you have?
Yeah, 6 and 7, and that one is with goat and dog. But it seems like we're doing the same thing here.
Same thing. Yeah, so 6 is you're going to do the exact same thing we just did, the point
Right.
criteria.
But between life satisfaction and type of animal.
Yep.
And then for 7, it would be the same thing. But
7,
switch
but-
it around.
The tricky thing about 7 is that you're not gonna do a bivariate correlation. You're gonna do a partial correlation.
Hmm.
So here, let me just open it up real quick. Obviously, I'm late for my next call, but whatever. Okay, so here's the goat and the dog one.
Mhm.
So the first one asks us to see if there's a correlation between, is there a correlation, life satisfaction and the type of animal you married? So a goat or a dog. It's so ridiculous. Okay, so you go to analyze, correlate, bivariate. It's your wife, that was the animal you're married to, and your life satisfaction. And then you leave it Pearson because we have a binary and then a continuous. Yes, there is a pretty strong correlation. So in other words, as one goes up, the other one goes up. So as you go from, let's see, how is the dog when measured? As you go from 1 to 2, your liking and life satisfaction increases. In other words, as you go from goat to dog. See, as you go from goat to dog, that's what that tells us. So if you're married to a goat, your life satisfaction is less than if you were married to a dog, which makes sense. Now, the tricky thing, or where it gets a little bit more sophisticated, is that 7 wants us to do the exact same thing, but take into account how much people like animals. That seems like an important third variable, right? Like it might not be the case that people are happier with life because they married a dog, if in fact you count for the fact, or count for the degree to which people like or dislike animals. It might be just the fact that people like animals. So to do that, when you go to analyze, you go to correlate, and you go to partial now. Same test, wife, life satisfaction, but you control for animal liking, and you hit OK. And it's the same result. You can see it's actually stronger now. The correlation increased from 0.63 to 0.7 after you control or hold constant how much people like animals, which is interesting. And this right here, what we just did, this partial correlation, is no different from regression. So we could have gone to regression, linear, and we could say, I want to predict your life satisfaction from whether or not you're married to a goat or a dog and your animal liking. You hit OK, and you can see here that what I get is essentially the same thing as my correlation coefficient, right? So that's what climbs us to regression really quick there. Okay. Okay, so I gotta end it for the day, but I say we go and celebrate Thanksgiving, and then we come back next week.
Okay, perfect. Can you also, where will you put this recording? Can you email it to us? Or is it?
Where's best? I could upload it to Sakai. I could upload it.
As long as we can get our hands on it to go through it again.
Yeah, how about emailing might be tough because it might be a big file.
Big.
But
Okay.
I can upload it to Sakai.
Sure, that's perfect.
Is that good?
Perfect.
Thank you so much for taking the time. Hopefully you're not too late for your meeting.
Yeah, I'm sure I could hop on. They're holding off for me, but
Okay, we'll let you go
Good
then.
luck. Happy
Yeah.
Thank you.
Thanksgiving.
thanks for reaching out. Well, I don't know who's
Thank you.
going to reach out to me next to set up the next meeting, but somebody will.
Perfect.
Okay.
We will.
Thank you.
Bye.